Okay, let's try this example again. Once again, 1,025 women were interviewed, randomly selected, the 48 lower states, continental United States. 47% of the women said they do not get enough time for themselves. We're supposed to construct and interpret a 90% confidence interval that estimates the proportion of women in the United States who do not feel they get enough time for themselves. Now, this poll found 47%. Let's see if it's going to fit and make things right. So, we wish to estimate a 90% confidence true proportion of women in the continental 48 states. We'll use a random one sample z-value, population proportion. The random sampling is in the statement. It was a random sample. 1,025, clearly less than 10% of women in the United States, lower 48, because 10 times that would be 10,000. 250, there's more than that. Large counts NP and NQ, or NP cap and Q cap, bigger than 10. Do the interval, that's P cap plus or minus the Z star sigma sub P cap. So the P cap is the 0.47, that's up here given to us in the problem, plus or minus 1.645. We got that from the 90% confidence we did before. You can look that up. Remember, 1.645 was for our 90% confidence interval, the Z star. The square root of PQ over N, the P 0.47, the Q is 1 minus that, and the N was 1,025, and you get this interval with the plus and minus, 0.444 to 0.496. Okay. Interpret the interval. We are 90% confident that the interval from 0.444 to 496 captures the true proportion. Remember, these statements, we always have them sort of sound the same, every single one. We have to put in the 90% and the interval, and which statistic, the true proportion, the true mean, and then use the statement of the problem to finish this. Women in the U.S., excluding Alaska and Hawaii, who feel they don't have enough time for themselves. So that's what we conclude from our 90% confidence interval. In the context of the problem, what 90% confidence means, in a large number of confidence intervals, if they were constructed, a large number, in this same way, about 90% of them would contain the true proportion of women in the United States who feel they don't have enough time for themselves. Suppose this poll was conducted by telephone calls made from 9 a.m. to 5 p.m. Maybe this method might result in bias. Speculate about this, I guess. Would it be biased? I say yes. 9 to 5 is when people are working. And perhaps those with jobs outside the home will not be able to answer that. It all depends upon how they did the telephone calls. And so this might be under or lower because they might be out working. Or, I guess that's what I would say. Let's see what it says. Women who work outside the home are unlikely to be home between 9 and 5. They would be underrepresented if we assume these were busier than those who do not work, or at least less likely to be alone at home some part of the day. Then we'll say that this estimate would be a little bit low. There would be more people because they would want some more time if they're out working. Just a guess. In planning a study, we want to choose a sample size that allows us to estimate the population proportion within a given margin of error. If you want to define the margin of error, then you can start sort of backwards. The margin of error, remember, is the z star times the standard error of the statistic, or the standard deviation of the statistic, found the same way, the margin of error. So Z star is that critical value. Because the margin of error involves a sample proportion p-cap, we have to guess somehow when choosing n. There are two ways to do this. Okay. Use the guess from before pilot study, or 0.5 is the worst case, the largest. So this would be for p-cap would be 0.5. So we want to choose a sample size that allows us to estimate a population proportion within a given margin of error. We set up this. We want this to be less than or equal to ME, the margin of error we're given. And then we solve for n. We're going to have to look up the Z star. We're going to have to somehow get the p-cap. And we're given the margin of error, so n is what we're looking for, finding how big our sample size should be. So let's try that. Company has received complaints about customer service. The managers intend to hire a consultant to carry out a survey of customers. But before contacting the consultant, the company wants some idea of the sample size that she'll be required to pay for. She'd like to have some knowledge. So if they say, yeah, we're just going to talk to one person, we need a bunch of money for that. No. One critical question is the degree of satisfaction with the company's customer service, measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, who are either satisfied or very satisfied, the two highest levels of the 5-point scale. She decides she wants to estimate within 3%, 0.03, at a 95% confidence level. You get to choose these this time. How large a sample is needed? Well, let's see. 0.03 is P. 95%. The critical value is 1.96. That's the Z star we found before. You're going to use this a lot. 95% confidence is used an awful lot. We have no idea about the true proportion, therefore, let's use p-cap, I don't know where this came from, as 0.5. Because the company president wants to be within 0.03, the margin of error, we need to solve this equation. The margin of error is less than 0.03, or at 1.96, the Z star, square root of p-cap, that 0.05 and 0.05 is less than or equal to 0.03, and solve for this n. So, I don't know why they didn't put the 0.05 or 0.5 in there anyway. Okay. Multiply both sides by the square root of n. Square both sides. Do the calculations. 1067, we better go up to 1068 just to make sure we are less than n. If n's got to be greater than that or equal to, and we can't have 1/10 of a person, we better go 1068. So, state and check random 10% large counts conditions for constructing a confidence interval. Determine critical values. Construct and interpret a confidence interval for a population proportion. Determine the sample size. We've done